So with that, I'll hand this off to, I believe, Cecile, who will give the introduction to our speaker. Go ahead, Cecile.
Hi, everyone. So this is Meghan Cronin, and she's from the NOAA Pacific Marine Environmental Lab in Seattle. She received her PhD in physical oceanography from the University of Rhode Island and her bachelor's from Columbia University. She was also co-chair of the inaugural U.S. CLIVA ISMIP panel in 2005 to 2008, and from that panel came a pretty important and key paper that outlined some of the best practice for process studies, including fair data, process study, and data access to synthesis product, etc. And we have the pleasure to have her today talk about the TPOS 2020 and beyond 2020. Thank you.
Thank you. Okay. Hello, everyone. This is an honor to be talking with you. Well, you know, working at home is kind of scary times here, but at the same time, doing these virtual meetings and webinars are kind of, sometimes they work, and I hope that this will work. So I'll be talking about TPOS 2020, beyond 2020. I've been involved in TPOS 2020 pretty much since, well, maybe not from exactly when it started, but I've been involved in both the first report and the second report and the report that's being worked on now. I've been the co-chair of the TPOS 2020 Planetary Boundary Layer Task Team and at the steering committee meetings, and have done a pilot study for sail drones use in TPOS 2020, or in the TPOS, which is the Tropical Pacific Observing System, by the way. And then there's also some pre-field process studies, and I'll be talking about that. So the slides I'll be showing are mainly slides that I got from Sandy Lucas, who's a program manager from NOAA, CPOC, the CLIVAR programs off there, and Billy Kessler and Anish. So getting started, TPOS, the Tropical Pacific Observing System. And the second report was, when the first report and the second report laid out what this strategy for the observing system should be, and how to optimize the observing system. The observing system had been, is right now mainly a set of about 70 moorings that were all in place by the early 1990s. And it's truly an outstanding array. But at this point, there's lots of new technologies. There's Argo, there's more satellites than there were in the 90s. So now we are looking at how to integrate all of these new, which are no longer new, but other observing system capabilities, like Argo, which gives you the horizontal, the vertical scales, and satellites that give you the horizontal scales, and use the moorings for where we really need to have the surface expression that cannot be done by the satellites, and the high temporal resolution, which is mainly in the mixed layer depth, mixed layer. So next slide. This is a figure from the second report, and on the left panel, you can see the capabilities of the present observing system for winds, winds and currents, surface currents, net surface heat flux. That includes both the turbulent heat fluxes and the radiative heat fluxes. That would be solar downwelling and long wave downwelling radiometers, and the CO2 flux capabilities. And on the right, we see what the capabilities will be with if the proposed array redesign is implemented. And so you can see that while there's some reduction in the winds, for example, which has caused a lot of angst amongst everyone involved, if implemented, there would be some new wind capability at higher latitudes, getting into the ITCZ and across the ITCZ, and then also some increased resolution here. Do you see when I'm moving the cursor? Anyway, I hope so.
Yeah, we see your cursor.
You see the cursor, okay. And then this Western Pacific part would be, has formerly been occupied by JAMSTEC with the Triton array, and for various reasons they are pulling out. And in this redesign, we're hoping that new partners with China would occupy this area, and that would extend up into the tropical cyclone alley there. I have to say that what I find super exciting about this new design is the mixed layer depth capabilities and the surface currents, which we have tier 1. We're thinking like tier 1 and a tier 2. But what I'm showing here mainly is on the right column are the tier 1, and that would include a current meter somewhere around 5 to 10 meters. Now, when push comes to shove and this gets implemented, and I think NOAA is moving forward to implement this, this is a really expensive part of the system, this surface currents, and they are going to push back. We know that they're going to push back and say, we cannot implement this in this year. This is going to take some time, a couple of years, or maybe do you really need to have all of this? And I really hope that the science community, that's you guys, will really argue and stand up for and explain the need for having current meters that are not just in the low wind regions where winds are, where the relative wind to the surface currents are different than the absolute winds, but also in the frontal regions of the cold tongue and the warm pool regions and other regions. So, the job is not done at this point. We still have to do a lot of advocacy for this array to make sure that what is being designed here is actually what gets implemented. Okay, now I want to explain in the TPOS-2020 think there are pilot studies, process studies, and sustained monitoring. And, back here, all of these dots are sustained monitoring. And there is existing technology of moorings and with current meter, seabird current meter, or certain seabird thermistors, or the kinds of technologies that they have been using for years and years and years. But there are other ways of getting these kind of variables, and that with emerging technologies like, say, for example, a prowler or sail drones or Argo floats with different types of sensor capabilities. And the way to raise their technical readiness level to the point where they can be part of the sustained observing system is through pilot studies. Process studies, on the other hand, are field studies where you where you resolve all of the processes and at the scales that they occur. And then from those process studies, you can determine what are the key variables that need to be monitored to resolve those processes. And then you can build that into the sustained observing system. So this slide was actually prepared by Sandy Lucas, who is the program manager at NOAA PMEL, the CLIVAR program. And I just said all of these things, but the point I want you to make is that the NOAA program manager made these slides about why we need to have a process study and field campaigns. And so that is really a key point here, is that there is a NOAA program manager who is interested in funding process studies in the tropical Pacific observing system. And she has, in fact, funded pre-field modeling experiments for this future process studies. And there was 8 model studies that started in 2018, and therefore 2 potential process studies. One was a Pacific upwelling and mixing physics study, and the other was air-sea interaction at the eastern edge of the Warm Pool. And these are the groups, and you can see that, you know, they're all different kinds of modeling groups, and they are, some of them are looking at the full Pacific, and some of them are eastern edge of the Warm Pool, air-sea, and some are pump studies. Okay, so just to talk a little bit about what a pump process study would be, these are some slides prepared by Billy Kessler. So let's see, the cold tongue is on the equator. The you get the let's see, how should I say it? So you have, I'm going to not talk about this teleconnections, because we actually know this. We know that when you have these temperature anomalies on the equator, they cause convection anomalies that then cause teleconnections that create warm and dry and wet and cool and all sorts of different anomalies all over the world. Okay, so what happens in the tropics affects climate and weather globally. Okay, so this upwelling here, we have this whole Walker circulation with cold water in the east. Okay, this is over by Galapagos, and the warm water. Okay, actually, we start with the trade winds blowing, and that then pushes up water, the warm water, into the the warm pool in the west, and then that causes convection, and you get this circulation. You have upwelling. Let's see. I'm not explaining this well at all. Okay, so then you get this circulation here, and there's lots of questions about the upwelling, because this upwelling that is associated with Ekman upwelling, because you got the trade winds on the equator. Let's see, that's not a good. The trade winds on the equator, you have the divergence and then upwelling, but that is has to be balanced by mixing of warm water downward to maintain this system. And so we have all these processes of tropical instability waves, the fronts, the upwelling, equatorial undercurrent variability, and when we try to model them, there's actually, you might get the equatorial undercurrent right, but when you look at the zonal currents off the equator, okay, so that's the blue here. That's what's going to give you a divergence on the equator and upwelling. You can see that each of these models is really different. And so that's going to give you a really different vertical velocity in each of these models. And so, and here's the observations of the zonal currents. So this process study would be looking at all of these processes on the equator that give rise to vertical velocity and divergence of the zonal and meridional currents. What am I saying? Did I say that the zonal? Okay. So, okay, I kind of screwed that up. I'm sorry, but I think that it's the meridional currents, but you can see that it's the meridional divergence that will give rise to the upwelling. But in any case, you can see that there's lots of variability in these different systems, and so that pump process study would look at what is giving rise to the vertical velocity. And these modeling studies are looking at what the scales of variability would be, and they're seeing all sorts of filaments associated with those tropical instability waves and other processes. So, okay, now on to the Eastern Pacific, the eastern edge of the warm pool process studies. And okay, so this cartoon shows some of the processes that are associated with this, the warm pool convection, and the shift in this front of you know, during El Niños, the warm water gets shifted to the east. Now, what is that boundary between the warm pool and the cold tongue? And you can see that there's it depends upon the salinity stratification, because you can get a salinity stratified mixed layer depth that then acts as a barrier to entrainment of cold water into the warm pool. And you can get formations of fronts, and then there's all sorts of variability that can happen on the thermocline. So here, Anish is showing that if you look at the barrier layers, okay, so this is the barrier layer between the mixed base of the mixed layer and the top of the thermocline. You look at that in the CSM, the coupled model, that's in the red, and you look at it in the ECMWF reanalyses, then there's big biases. Now, this is a reanalysis in black, and really, what is the observations? A field program would be able to look at this with observations. And you can see, let's see, in this slide here, this is looking at the actual barrier layer. So this is the barrier layer thickness in the top, and this is how it's related to the mixed layer depth versus the isothermal layer depth in the dashes. So lots of biases there in the model, which is the red versus the reanalyses, which is in black. And what Anish is saying here is that these model errors can potentially lead to expensive errors in the weather forecasts if they cause changes in this deep convection and variability, and its shift across the equator and the teleconnections to other parts of the world. And then finally, here's a slide. He's saying that all of these processes, these air-sea interactions, have multiple time scales and length scales. And so, for example, this is a figure from Carol Ann Clayson, where, she's running a 1D model and with different vertical resolution. And the blue here, the blues are a high resolution, like centimeter to 1 meter to 2 meter, as you go deeper into the water column, versus 1 meter resolution in the orange, a 1 meter resolution 1D model, and a 5 meter resolution. And so for the 5 meter resolution, 5 meters is the top top level. So this is the 5 meter temperature, sea surface temperature, versus the dark blue is the 5 meter sea surface temperature from this high resolution 1D model. Forcing is the same, model physics are the same. The only difference is the vertical resolution. So that is a remarkable result, that just changing the vertical resolution gives you this rectification of the high frequency into a lower frequency warming here. But there are other kinds of variabilities, and MJOs and Kelvin waves and barrier layers, and this is a model output from Shui Chen. And so whereas the pump upwelling would be looking at processes over in the Western Pacific here, and the upwelling and mixing, here, this eastern edge of the warm pool air-sea interaction study would be looking at the processes in this area here around the date line, and where you get all of this kind of warming that happens through lots of different processes, air-sea interaction, coupled with the barrier layers and the Kelvin waves. Okay, so here we are. How am I doing on time? Let's see.
If you can start wrapping it up, that way.
Yeah, I am. Okay, so here we are in time. I'm sorry about that. I didn't have a clock here. We're at here, and they're hoping to have a US CLIVAR workshop. There's been one proposed for spring 2021, and then the field program would likely be fall 2021, and then in the water by summer 2023. And so Charlotte DeMott and Anish have proposed this US CLIVAR workshop to get all of the ideas juiced up, and there would be plenary talks and breakout sessions. So I'll just end with that. I'll go back to here with ending that. And sorry for going over my time. Any questions?
No worries on going over time. So if you have a question, reminder to take yourself off mute and just ask it out loud, or you can type it in the chat box, which you can access in the top right corner.
Hi, Megan. This is Antonietta Caputondi. Hi. So I have a question concerning pump. So you said that the pump is supposed to look at the processes that affect the upwelling in the Eastern Pacific. So the subtropical tropical cells have been related to changes in upwelling. And so is this program also, this process study also going to look at the equatorward transport in the interior?
I would think it would have to.
Okay.
I think that's a big part of it.
Yeah. Mm-hmm.
But it's those kind of questions that are trying to be scoped out right now.
Okay.
Okay.
Any other questions?
Actually, I have another question, if it's possible. So, how have you decided about how this implementation, the implementation plan of the new array is going to happen? How is that proceeding? So what is the time scale, or what is going to happen fast?
What's going to happen first for the implementation, you're saying?
Yes.
Well, what I hope is not going to happen is that they I think that they're not going to pull out moorings first. Their plan is that they're going to, at least pre-COVID-19, the plan was that they would keep everything and then start putting in the new measurements and run the operational models with the new and with the old so that they can see what the improvements are from having it. Now, I think that the easiest things was to add some of the temperature sensors and radiometers. The current meters are hard because they require a different data logger system for it. And so, in fact, it's not just the current meter cost, it's also the data logger cost that has to go in. And I think that that is probably, giving them pause with it. But, technology is always changing, and they're going to need to get these new data loggers. So, that just might be pushing things forward, I think. It's a matter of how you do bookkeeping, though, whether you say then that is also part of the cost of the current meters.
Thank you.
We have a question from Isabella Labras on the chat box. She asked, going back to the proposed observations, you mentioned that the new current meters are a particularly expensive component. Is this due to equipment costs? It seems like a cost-effective way to gain understanding if the moorings are going out already.
Yeah. Okay. So I kind of just answered that. It's not just they are one of the most expensive sensors, but it's also this data logger issue that's a problem. But I personally think that it's a really important measurement because, on the equator, the flow is not geostrophic. You cannot just use the, dynamic height to calculate what the currents are. And also the winds, we need to know what the winds are relative to the currents. And in the cold tongue region, the winds can be very weak. And, we do know from Shelton Dudley's work and lots of other work that the cold tongue front does impact the winds. And I think that we really, to know what that forcing is, we need to know the relative winds. We need to know the surface currents and the absolute winds.
Thank you, Megan. This is Isabella. Just to follow up. So are those loggers necessary for getting the data back in real time?
Yes.
Okay. Thank you.
Yeah.
Megan, this is Chanelipo. Can you hear me?
Yep.
So at the beginning, you were excited to mention that mixed layer depth would be a new parameter available from maybe the new configuration or the proposed configuration. So can you explain again, why would that be compared to the previous configuration? What novelty in the mooring would allow that?
Right. So previously, the vertical resolution is every 20 meters. And that was decided in the 80s. And it was because what they really wanted to know was sea surface temperature and the depth of the thermocline. And they didn't really care about mixed layer depth. There's no way that you can calculate mixed layer depth with that kind of resolution. Whereas in the proposed, it would have 5-meter resolution in the top 30 meters. So you could get the mixed layer depth. And the reason we want to know the mixed layer depth is because that tells you how the heat gets how much heat gets applied to the ocean, and it acts as like a effective heat capacity. And so the sensitivity of the warming, if you have a certain amount of heat that goes into the ocean, what is the sensitivity for how that heat then gets transferred into a temperature change depends upon that mixed layer depth, which then affects the effective heat capacity. Does that answer it?
Yes, of course. So I just want to follow up. So you could get some large-scale maps of mixed layer depth, like every 10 days from Argo. Do you need something, at smaller spatial and temporal resolution than that?
You do need it at smaller temporal resolution because, in fact, that mixed layer depth varies diurnally and associated with wind events and storm events, which happen much more rapidly than 10 days. And so a 10-day mixed layer depth is going to be seriously aliased.
Great, thank you very much. That makes sense.
Thanks.
Megan, this is Sergey from. I have missed one important part. Do you propose to have just a thermistor chain in the upper ocean to get to the mixed layer depths, or the CTD chain?
That's an important point. And in fact, that's not shown in this map, is it? Because that's one of the fuzzy points still that needs to be determined, is where are the salinity measurements going to be? And so that's still to be determined, and they're trying to figure that out. Most likely, the salinity measurements would be in the ITCZ region and the Western Pacific region, and there's question about whether it should be along the equator even. The Argo float is going to give us salinity. So really, it's a question of where do we need salinity to give us a mixed layer depth? And that then becomes a question of where do those barrier layers happen? And I suppose that that's part of this question from the process study, that those barrier layers, where do the barrier layers happen? Where do we need to monitor that? That's where we need to get the salinity.
And I think we have one more question on the chat box before we probably should end this webinar. Monique asks, you probably said it and missed it, sorry, but is the only difference between Tier 1 and Tier 2 the ADCP? Where would Tier 2 be available? Thanks.
Yeah, thank you for that question. Right, because I kind of slid over that. So we have, through these pilot studies, we have developed a capability of having real-time acoustic Doppler current profiler measurements that are attached to the mooring, and therefore measure the profiles up to like 10 meters or so, 7-10 meters. And this is really a game changer in the ADCP time series world for the TPOS, because previously these were just measured at 4 sites and in delayed mode, and their top depth was at 30 meters or so, and therefore missing all of that secondary circulation cell that Antoinette was talking about. And so where would they go? We're thinking probably at those 4 sites, the historical sites, but also maybe off the equator at one longitude that would be monitoring the upwelling. And so this would be determined by this pump experiment process study, but potentially it could be at 140 and maybe at 0 and 1 meter, 1 north, 2 north, 1 south, 2 south. But again, that's one of the fuzzy areas that a process study will help.
This is Monique. Thanks for the answer. Just to make sure I understand, does that mean there will be no information on currents below the ADCP, like the 70 meters?
And so there was actually a pilot study trying out having multiple of these profilers. So it had 4 of them, so that they it was a daisy chain set of these mounted profilers down to 250 meters, and that would then replace the second mooring with the upward-looking profiler, and it would give real-time profiles down to 250 meters.
Okay. Can you please remind me what time the undercurrent is? What depth the undercurrent is along the equator? Because it's I don't remember how deep it goes. I thought it was below 70 meters.
Yeah.
That's what I was asking.
Do I have It's kind of the this doesn't show it, does it? It's deeper in the west, and I think in the west, I'm thinking, below 150 to like 250, and then in the east it gets shallower and is, I think, is between 100 and 150 or so. I'm thinking.
Okay, so it does sound like you would need, those chains you were talking about to resolve that undercurrent. Okay.
Yep.
All right. Thank you.
Okay, great. So it's looking at my clock, it's 12:41. So I think we're going to end the webinar series here. So thank you, Meghan, for presenting, and thank you everyone else for joining us on this webinar and for your discussion. So it seems like we have a lot of great discussion. So if anyone has any questions, is it okay if they reach out to you, Meghan?
Absolutely, would love it. And sorry I went over there.
No worries. That's great. So once again, I want to thank everyone for joining us today, and I'll send a recording of this webinar through my email. It'll also be posted on the US Cliver YouTube channel. Our next POS panel webinar series will be on June 4th, and it'll feature Lisa Beal on Induce. So thank you, everyone. Have a good day.
Thank you.
Thank you, Meghan.
Thank you. Thanks,
Bye.
Meghan.
Bye.